I'm here with a company called 3Scan, who does this kind of new thing we started recently calling volumetric cloud histology. I'm the CTO and co-founder there, and today I'm going to take you on a little bit of a tour of, first of all, a little bit of what histology is, because you're a little bit more like kind of computer science focused folks, and then talk about some of the weird elements that we bring to it. So trivia points, does anybody know the person on the right here? Sorry, my left, your right. The guy in black and white. What's that? Very close. It is a contemporary. This is actually Ramon Cajal. He's one of the first people who looked through a microscope and actually drew what he saw. This was a major innovation over the last 200 years of biologists who stared through little pieces of polished glass and didn't draw anything. So the thing that's kind of astounding is that the other person in this photo is one of our lab technicians, and the instrumentation that they're both using looks remarkably similar, like maybe even distressingly similar. And the thing that's kind of really frustrating is that there's 130 years that have elapsed between these two photographs. Like, if we accepted that as the way in which technology advanced, it would be like Tesla came out with this as an automobile. This is just like not okay. It really just isn't okay. So this kind of motivates a little bit of what our company's been working on. I'm a little bit short selling the field. The thing that has actually changed during that time is the degree of skill you need to do this has dropped precipitously. In the 19th century, you had to be basically an independently wealthy gentleman scientist, and in the 2000s, you need to have gone to a 2-year degree program. That's just kind of like not even like a college thing. So one of the things that's kind of interesting is anytime your job description changes twice in your lifetime, you should be afraid that the robots are coming for you. So all those people out there who are new into data science, it's a rebranding of computer science, so don't worry too much. But we build histo-robotics, really, so it's kind of the next logical step in this progression of de-skilling, really, a thing that was very artisanal and then has moved down the chain towards robot work. So these are kind of what our histological robots look like. They're kind of large, ugly, kind of Doctor Who-style phone booths. But inside of them, they have some fairly sophisticated equipment. You'll see in here, oh, it fell off the side. That's great. So that little blue wedge in the middle is actually a diamond knife. So there's a 5-millimeter wedge of monolithic diamond at the center of these devices. And we use that to carefully chew up blocks of tissue. And while we're doing that, we're simultaneously imaging them. It's a really important piece of the core tech, but the important motivation for you here is that we've got a 3-dimensional piece of tissue that we're progressively slicing into thin sections and turning into ones and zeros. That's really all there is to it, and I'm not going to belabor it too much longer than that. The thing that's interesting and what makes this really challenging is that these objects have an incredibly high data rate. We basically take something like a 1 gigapixel image every second for each one of our microscopes, and on average we have 7 of them running for an average of about 8.5 hours a day. That's largely limited by the fact we have only a single shift of people who monitor and do upkeep on them. So we're probably going to change that in the next quarter, but it depends on some other things too, because the logistics of that turn out to be really hairy. So yeah, the statistics I just gave you. The other thing is this is destructive. Fundamentally, we are plowing a knife into a piece of tissue and destroying it, and when we're done with it, it is gone. And it actually gets sucked into a thing we jokingly call the archive, which is a filter. And then you get this big ball of bio-mush at the end. You don't want anything to do with it. But there's no second chances. So we had to build an architecture around it that was incredibly durable and also incredibly high throughput. So, oh, and this is one other really horrible side effect of all of this. If we were to digitize a centimeter cubed of tissue, the amount of physical space it takes up in terms of spinning disk hard drives is 2.5 times larger than the tissue itself. This is terrible because it means for every sample you get in the mail, you need to have that much more hard drive physical space. So we spent the first couple of years running RAID arrays and trying to deal with ZFS and this whole other horrible nightmare that I will completely not expose you to. But the long and short is that we've gotten a much better handle on that throughput recently. And to give you a sense of the sample size and scale, a single data set is that little blue square up on the top left. It's about 2 terabytes. The largest open source image data set that's been really popular for a bunch of deep learning is about 3 terabytes. And then the blue lines there are the ones that we've captured last quarter. So frankly, this has only really been possible because of Amazon. And like the core of our business offering is actually meat indexing service. This is gonna sound really ridiculous. But like this is actually like, it took me a while to discover this was the core value add that we had, is that we had this piece of tissue and then we had spatial information that was coherently kept over time. And I'm gonna kind of walk you through just a little bit of how we've kind of managed to do that. The metaphor here is that at the base we have these things called atoms. They're the indivisible piece of the world. They're like a little tiny, they're a little tiny piece of imagery or other things maybe. We arrange them physically in a three-dimensional space that we kind of embody through S3 we'll discover. One other thing that became important to us early on, this is a little scattered, I'm sorry, is that we actually need 4 dimensions because it's really important for us to be able to acknowledge zoom. This is a really common thing in Google Maps, for example. You want to be able to look at the small picture or zoom out and take a look at the whole picture. We need that same analog in a 3D space. So we fundamentally built a n-dimensional index on top of S3 and Dynamo from you all here. I can go into the nitty-gritty of this for any one person who's particularly interested. I've got an architecture diagram, I think, next, but it's frankly, it's not very helpful. But the long and short is that we use Dynamo as a live index, and then we use S3 keys as an index that it talks into. If anybody ever wants to talk about reading into chunks of S3 keys and some of the weirdnesses that come with that, hit me up later. There's a whole weird side story there I could tell you. But the long and short is that we end up with these spatially built compute products. And anything that's serializable we can kind of put into this framework. And this leads to like actually a really kind of fun situation. So we've got this n-dimensional mapping function you can use to take an arbitrary function, map it over an image space and return JSON or another image or you name it. We've got another form of it that's padded. This is really popular for people doing deep learning type stuff because it takes away the edge effects. So you have a nice big mosaic of imagery. You load up your deep learning, you run your little thing, then you crop out your classification in the middle. It feels really good. Another one you can do is you can actually do sampling and size changes. This is kind of interesting. This takes a little bit of mental arithmetic and difficult accounting to get your head around, but it turns out this is really important if you want to, like, for example, downsample something or do level of details or traditional image processing type pyramid work. It comes up right away. And you can also do all of these other things that kind of NumPy comes with, full batteries, if you know what that means, in terms of fancy indexing and squashing kind of various axes and dimensions. So in the same way that you have a n-dimensional mapping framework, we also have an n-dimensional reduction framework. So that's kind of interesting. It turns out being absolutely important. The thing that's most important about all of this is when you break up the problem this way, it's trivially parallel. You can load up your 500 different containers. They can all be running. They sign up for a little work queue, and they turn through things and put things out on the other side. So that's what actually allows us to get through any amount of imagery day to day. Because when you're capturing tens of terabytes per day, your analysis will get behind immediately if you're not processing just as fast as you're putting data into your store. So otherwise, like hoarding data has zero value. You need to be doing some form of analysis. I didn't talk about what our products were here, just a little bit. The one thing that's really powerful about this approach is it forces you to separate your process algebra, which I mean like the composition of these large level functions like plus and division, from your like actual functions that are being written at the bottom. You really don't want your analysis people playing with S3 keys, and you really don't want your infrastructure people on the other side. So this has actually been a very, very functional division for us. And similarly, you can take this like multiple input to single output and single input to like multiple output, which gives you this full category theoretic good feeling, if that speaks to anybody. I wanted to thank, before I disappear off the stage here, Elliot for putting all this together, because he's been a total rock star. I'll show a couple of videos at the end, which is kind of fun. I'm standing on the shoulder of a bunch of great giants from my team. They're total rock stars. They made all of this. I just come to conferences and talk about it at some interval. And the other thing I think is really interesting, it's largely driven by people in this room, is that now there's a discussion around cloud laboratories. Fundamentally, we're only a service model. We take in tissue and output data. So we're kind of a physical form of the Amazon snowball, if you're aware of that. It's just you can nail in pieces of who knows what and get ones and zeros out the other side. So there's kind of an interesting transition going on, and I think all of you all are a big piece of that right now. But yeah, let me show a video. So why are we doing all this? The real reality is that we've got this kind of like neat 3D data sources that come out, and there's a lot of richness there. Come on. And I could show videos all day, but like kind of having some sense of what we do, that's all the fun people come and talk to me. So this is a cross-section of a piece of lung. You can see the airways in black. We've done a very naive segmentation, basically percentage pink, you can think about it that way. And as you stack up more and more and more of these serial sections, you start seeing the overall 3D ultrastructure. You've got the big airway coming through and all the branching alveolar passageways off of there. So, you know, it's what we do, it's what we love. And if you've got weird biology you want scanned, let me know. So, thanks guys. Got like 2 minutes? Yeah. Hit me. All right. No? No, it's fine. Yeah, please.
What was the connection with the meat?
Oh, sorry. This is a silly metaphor at the last minute, honestly. Really, what we provide as value is not that we image tissue, it's that we have a concrete idea of where things are in space. So in the same way you'd say, like, this is a piece of tenderloin, you can say, this is stage 2 Gleason score cancer. And I try not to say the C word in mixed company, kind of jokingly. But a lot of what we do is informing various treatment modes. So while we built all this neat infrastructure to do all this neat n-dimensional indexing, the core outcome is, what is this meat and where is it? Is kind of the various forms of question permutation we get that we try to serve. Does that help, or? Okay, cool.
Any other questions? All right, thank you, Matt.
Thanks, guys.